or comparing and graphing linear functions. So some of them are linear, some of them aren't. So we're going to try and see if we can figure out how to tell the difference. Now, on one of our recent assignments, we were given a graph like this, and all these points line up on a straight line, and we were asked to write a function for that, or an equation. So we looked at it and said, okay, well, first of all, we know that the y-intercept is 3. So b equals 3. And we know that the slope is down 1 over 2. So the slope was down 1 because the change in y goes on the top of your fraction and the change in x goes on the bottom. So then we write our equation, y equals the slope multiplied by x plus or minus the y-intercept. Plus if it's positive, minus if it's negative. All right, very good. Okay, what about this next one? Well, instead of a graph, we actually have a table of values, and we notice that we don't have a 0 on the x column, and that's one of the things we were looking for yesterday or on our last assignment. So we got to kind of look at this pattern. We go up by 1, up by 1, up by 1. So if I go down in the opposite direction by 1, that would put me at 0. And I notice that these numbers are going up by 9 each time. So if I go in the opposite direction, if I'm starting at 9 and I go down by 9, that's going to put me at 0. So that's going to mean that my y-intercept is at 0. Now my slope, we've kind of alluded to it, change in y is 9. Change in x is 1. So my slope is just 9. And my equation then would be y equals 9x. And that's it. No plus or minus on the end because the y-intercept was 0. Okay, very good. So let's move along then. So today we're going to kind of compare the difference between linear and nonlinear functions. A linear function has a constant rate of change or a slope, and the graph is a straight line. So that's the easiest way to tell is if it's a straight line. But if you don't have the line, you just have the set of ordered pairs, you can tell by seeing if it has a constant rate of change, which we will show you shortly. If it's a nonlinear function, that means it doesn't have a constant rate of change, and the graph is not a straight line. It might be a curve or a V-shape, something like that. So for example, if I give you a couple of graphs and say, is this graph represent a linear or nonlinear function? The answer to the first one is no, because it has a curve to it. It's a curved line. Okay. The second one is a straight line, and so that would make it linear because it is a straight horizontal line. Now, if it had been a straight vertical line, even though it's a straight line, that's not considered a linear function because it has an undefined slope. All right, this one is a V shape. And if we remember our vertical line test, a vertical line only hits it once at any one location. So it is, so it's a function, but it is not linear. So no, not linear or non-linear. This one is a straight line. It's got a nice slope to it, pretty steep slope. So yes, this is a linear function or a representation of one in graphic form. So let's kind of summarize then. Linear functions have two variables like x and y. They can be solved and written in y equals mx plus or minus b form. The line or the graph of the line would be straight. There's no vertical lines. There's a constant rate of change or slope. And quite often, as you're looking at the pattern, you're kind of adding or subtracting the same amount each time. as you look at the table of values. For nonlinear functions, the graph is not a straight line. It does not have a constant rate of change or slope. You don't add or subtract the same amount each time on your table of values. You do multiply or divide by the same amount. And the graph, like we mentioned, is not a straight line, so I kind of reiterate that twice. And x can have a power bigger than 1. So if you have y equals x, for example, in order for this to be nonlinear, you have to have a power on that x so that it causes the line to change shape and not be a straight line. All right, so based on that little review, let's check. Linear equations are a nonlinear line. This equation would represent a nonlinear function because it has an x squared in it. Okay, a linear is can't be a vertical straight line. A nonlinear doesn't have a constant slope. The slope is changing. Nonlinear is also a vertical line. Constant rate of change, y equals mx plus b. It's a straight line, and a circle would classify as a nonlinear function. So there's a good way to kind of sort out whether or not we're starting to get this. Okay, so now let's take a look at this table of values. What we need to determine is if there's a constant rate of change as we go through the tables. So let's take a look. All we got to do is check our changes in y and changes in x. So to go from 40 to 32 in the y direction, I'm subtracting 8. To go from 32 to 24, subtracting 8. And from 24 to 16, we subtract 8 again. So that's a constant rate of change. What about on our x values? We go from 3 to 6, that's an increase of 3. 6 to 9, 3. 9 to 12, another increase of 3. So our change in y over the change in x is negative 8/3, and it's a constant rate of change. Meanwhile, the next one has a change of y, which in the first one is plus 9. But in our second step, we go up 22. Our third step in our change in y is up 55. So as you can see, it's increasing rather dramatically. So this is not a constant rate of change, so this is nonlinear. All right, let's move on. Couple more. Does the table represent a linear or nonlinear function? So let's pick it up. Plus 2, plus 2, plus 2 in the x direction. Minus 4, minus 4, and minus 4 in the y direction. So minus 4. So that would be a slope, and you can see they're all the same. Change in y over the change in x is a constant rate of change. It's the same amount each step. So yes, that's linear. All right, how about this one? 4 to 8, 8 to 12, 8 to 6, or 12 to 16. So we're going up by 4 each time on this one. Here we're going up by 1, up by 1. And then the last one is up by 1. So our constant rate of change is 4 over 1, or just 4, right? So we got a slope. How about this last one here? In the y direction, we go from 21 to 15 to 5. So when I go from 21 down to 15, that's a decrease of 6. From 15 to 10, that's a decrease of 5. And from 10 to 6, that's a decrease of 4. So there may be some kind of a pattern going here, but it's not a linear pattern. And the change in x is minus 1, minus 1, minus 1. So we're going down by 1 each time in that section. So nonlinear.
Teachers, before you take off, just a reminder that tomorrow we'll be doing the panorama survey. I sent out an email, and then the students will get an email tomorrow right before reading time. So we'll We want to make sure that we get that taken care of tomorrow. If it goes over, we'll finish it on Friday. Thank you.
Okay, so moving along, when you get to Alex, it's going to look something like this. So you'll just look at your X values. There's a change in those of 4. My Y values, -2 to -1, that's an increase of 1. From -1 to 0, that's an increase of 1. From 0 to 1, an increase of 1. So it's a constant rate of change, so it's linear. This one can go from -3 to -2, -2 to -1. So in the X direction, we're adding 1 each time. In the Y direction, -5 to -7, that's down 2. -7 to -9, that's down 2. And -9 to 11, that's down 3. Okay, so that looks like a constant rate of change, so that would be linear as well. All right, let's look at these. A constant rate of change or not. So -2, -1, and then this would be -3. So the change in Y right off the bat is not the same each time, even though on the X side we're going up by 1 each time. So this would be nonlinear. All right, let's look at this one. Oh my goodness, the change in Y there is no change in Y. It stays 0, but there is a change in X. So that's still a constant rate of change. So that would still be linear. Okay, now we're going to just practice graphing a few of these functions. And there's a couple ways to do it. We could just use the slope and the y-intercept. So we could go to -6 and make a dot. And then go up 2 and over 1 a couple of times. So if I do that, then I've got that one, and then up 2 over 1, up 2 over 1. So we've done this before where we just plot out a couple of points and draw the line, right? The other option is to just plug in some numbers. So if I plug in 0 for X, and 2 for X, and 3 for X. 0 in for X would be 2 times 0 minus 6, so that would be -6. And then if we put in 2, 2 times 2 is 4, 4 minus 6 is -2. And 2 times 3 is 6, 6 minus 6 is 0. And so if we start plotting those points, we got 3, 0, 2, -2, and 0, -6. We notice right away that we have the same points that we had earlier mentioned and drawn on the graph, so we know we're in good shape. Okay, how about this one? Let's plug in some values. Let's try, I always like to pick the small numbers because they're near the origin and it's just easy to graph them. So if I put in 0 for X, -4 times 0 would be 0. If I put in 1 there, -4 times 1, what would that be? -4 times 1 would be -4, right? How about -4 times 2? So this would be -4. -4 times 2 would be -8. So we know right away we got 0, 0, 1, and -4. -1 and +4. Sorry, -1 and 1, 2, 3, 4. And 2 and -8. 1, 2, 3. So you notice they lined up in a straight line. That means it is linear. All right, let's move along. Let's check out another one. Okay, so this has got a slope and a y-intercept. So let's go ahead and graph this one. And because it has a fraction with a 5 in the denominator. We're going to use 0, and then we're going to use 5 and negative 5 for our x values, because these will help simplify this fraction quite well. So if I put in 0 for x, 0 times negative 1/5 is 0. 0 plus 3 is 3. If I put in 5, negative 1/5 times 5, negative 1/5 times 5 would be negative 1. Negative 1 plus 3 is 2. If I put in negative 5, negative 1/5 times negative 5 would make that a positive 1. And 1 plus 3 is 4. So there you go. So would this be linear? 0 and 3, 5 and 2, negative 5, and 1, 2, 3, 4. Sure enough, look at how they line up on a nice straight line. So that one worked out quite well. So your assignment is number 73, comparing and graphing linear functions. Good luck.